Welcome back, Eduvo students. I am absolutely thrilled to have you here for our explainer on the final section of Chapter 12. So, as your lecturer, I want to take you through a frankly fascinating part of software engineering. Look, up until now, we've talked a lot about designing and building systems. But here's the reality check. Once you build a safety-critical system, you can't just release it into the wild and hope for the best. You have to definitively prove it's safe. And that is exactly what we're going to be focusing on today. So, let's dive right in.
Here's our quick roadmap for the session. We'll start with an introduction to safety cases, define them, look at building a structured argument, and dive into software safety arguments. Then we'll tackle proof by contradiction, and finally, wrap the whole thing up with a Chapter 12 exam summary.
All right, Section 1, Introduction to Safety Cases. Let's talk about the real-world stakes here.
I want to pose a pretty essential question to you all. How do you actually convince a government regulator that a safety-critical system is safe to deploy? Now, a regulator is an external government body whose entire job is to protect public safety, or the environment, or the economy from dangerous systems. Think about it. If you're building an aircraft control program, or, say, software for a nuclear reactor, honestly, writing reliable code is completely useless if you can't legally prove to these regulators that it's safe to operate. They simply won't let your system launch. No proof, no launch.
Okay, Section 2, Defining a Safety Case. Let's strictly define our terms before we go any further.
The textbook gives us this brilliant definition from Bishop and Bloomfield. A safety case is, quote, a documented body of evidence that provides a convincing and valid argument that a system is adequately safe for a given application in a given environment. Now, the really interesting part of this is the phrase body of evidence. A safety case isn't just a bunch of code. It's an expensive, massive portfolio of proof. In fact, just compiling this documentation can sometimes cost as much as developing the software itself.
So, what exactly goes into this massive portfolio? Well, it's a mix of physical and procedural elements. You've got your hazard analysis and logs, which track every single potential danger. It includes all your test results, your static program analyses. It even includes incredibly detailed documentation of the development processes you used, plus the records of your review meetings. The crucial takeaway here? Even proving that your engineering team was highly competent and followed strict procedures, that is a fundamental part of the safety case.
Right, moving on to Section 3, Building a Structured Argument. Let's look at the logical structure of all this. To convince a regulator, you can't just hand them a pile of papers. We need to carefully scaffold a hierarchy of structured arguments. There are 3 core steps to this. First, the claim. This is a clear assertion of safety, like saying, this system will not fail under X conditions. Second, the argument. Think of this as the logical bridge explaining exactly why the claim is true based on the data. And third, the evidence. This is the hard data, the physical proof that actively supports your argument.
Just picturing how this flows, we always start from the foundation of our evidence. That concrete evidence structurally supports the argument in the middle. And then that argument is what logically justifies the higher-level safety claim at the very top. It's a straight line of irrefutable logic.
Let's map this theoretical structure directly onto a concrete scenario, just so you can see how the logic operates in a real medical device. We'll use the textbook's insulin pump example. Our top-level claim here is the pump will not deliver an insulin overdose. The argument bridging to that claim is the maximum computed dose equals the max dose limit, which basically means mathematically the software cannot ask for too much insulin. And finally, our evidence supporting that argument, 400 test cases passed, and static analysis of the program code found 0 anomalies affecting the current dose variable. By linking these 3 together, we build an undeniable proof of safety.
Section 4, Software Safety Arguments. Let's apply this directly to the code.
Okay, I really need to address a major misconception that students often have here. You might think safety engineering means you have to prove the entire program works perfectly under all conditions. Honestly, proving total correctness is way too expensive, time-consuming, and complex. We just don't do it. Instead, the reality is that we only care about mathematically proving specific hazards are impossible. Proving an unsafe state cannot be reached is significantly cheaper and highly, highly effective.
To do this, we use 4 explicit steps to construct a software safety argument. Step 1, we deliberately assume that an unsafe state has actually been reached. Step 2, we write a predicate defining this unsafe state. Now, a predicate is simply a logical expression or a mathematical condition, something like variable x is greater than 10. Step 3, we analyze the code backwards from that point to find a logical contradiction. And step 4, we just repeat this process for all the identified hazards.
So let's briefly recap this crucial takeaway, because it's guaranteed to come up again. Software safety arguments are so much cheaper to make than absolute correctness arguments simply because you only focus on the hazards. You ignore the safe paths completely, and you put all your engineering energy into proving the dangerous paths lead to mathematical contradictions.
Which brings us to Section 5, Proof by Contradiction. Time for the mathematical proofs. Let's look at the unsafe predicate for our insulin pump. The absolute worst possible hazard here is an overdose. So, our predicate is current dose is greater than max dose. Our goal now is to mathematically assume this terrible, fatal state has actually happened and then work backwards through the code to prove it's actually impossible.
So, if we analyze the code paths immediately before the administer insulin command is executed, we start with our unsafe precondition, current dose is greater than max dose. Now, if we follow the logic backwards, the last assignments to current dose in the code are either current dose equals 0 or current dose equals max dose. Let's test them. If we take current dose equals 0, does 0 equal a number greater than max dose? No, absolutely not. That is a contradiction. What if we take current dose equals max dose? Does max dose equal a number greater than max dose? No, another contradiction, because all possible code paths lead to a mathematical contradiction. Reaching the unsafe state is literally impossible. The program is safe.
Okay, take a cognitive breather for a second. That was heavy logic. Why do we work backwards? Summarizing the textbook, working backwards is the absolute secret to this technique, because it allows us to completely ignore all the intermediate states and complex logic earlier in the program. We focus strictly on the final variable assignments just before the critical execution. It radically simplifies the whole mathematical proof.
All right, Section 6, Chapter 12, Exam Summary. Time for our capstone review.
Okay, students, take a deep breath, grab your pens, and get ready for a rapid-fire recap.
From Sections 12.1 and 12.2, you must remember the core difference between safety and reliability. A highly reliable system can still be highly unsafe if the original specifications were just wrong. You also need to know Pero's theory of normal accidents, which states that in highly complex systems, anticipated combinations of failures are inevitable. Remember the hazard-driven requirements, particularly the risk triangle and ALRRP, which stands for as low as reasonably practical. And finally, know how to use fault tree analysis, which is a top-down deductive technique for analyzing hazards.
Continuing the recap for Section 12.3, you need to deeply understand safety processes. The most critical document here is the hazard register. That is your central traceability document tracking every single risk. You also need to know the verification techniques: formal verification, model checking, which is an exhaustive state analysis using specialized tools, and static program analysis, where tools scan the source code for anomalies without actually executing its behavior. These are guaranteed exam topics. For your tests, ensure you can accurately define a safety case, map out a structured argument from claim to evidence, and explain exactly how a proof by contradiction works in safety engineering.
Well, we have covered incredible ground today. We've learned how documenting safety is just as vital as engineering it, and how to mathematically prove a system is safe from accidental hazards. But I want to leave you with a provocative thought before we go. We know how to stop the insulin pump from accidentally overdosing a patient, but how do we protect it if a malicious hacker actively tries to bypass our defense and alter the code? That thrilling question perfectly sets up your very next syllabus topic, security engineering. Thank you so much for joining me for this session. Study hard, and I will see you in the next explainer.